In section 2.5, we're going to discuss infinite limits. Let's consider the function f of x, which is equal to 3 divided by x minus 2. This is a function that we know would be undefined when x equals to 2. If you try to plug 2 in, we would get a division by 0. So we know it's not defined at x equals to 2. Let's see with a numerical approach what happens to the function values near this disallowed value of x equals to 2. So on a number line, if we kind of approach 2, first coming from the left-hand side, these would be approaching values of 2 that are slightly less than 2. So we could take a sequence of x's like, let's say 1.5, 1.9, 1.99, etc. One of the things that we notice is that as we get closer to 2, the outputs we get are getting larger and larger and larger negatively and are kind of decreasing without bound. If we look at what's happening as we approach 2 coming in from the right-hand side, these would be approaching 2 from values that are slightly greater than 2, things like 2.5, 2.1, etc. And as we get closer and closer to 2, what we see is that, again, the functions are positive, and the function values are positive, and they become unbounded. So as x approaches to 2 from the left, what we observe is that the function is approaching negative infinity. As we approach 2 coming in from the right-hand side, we see that the function is approaching positive infinity. And we can kind of represent this with the limit notation. We will write that the limit as x approaches to 2 from the left of 3 divided by x minus 2 is negative infinity. And we will also write that the limit as x approaches to 2 from the right of this function equals to positive infinity. Again, in the truest sense of the words, technically these one-sided limits would not exist because we do not get a real number. Negative infinity and positive infinity are not real numbers. However, at least if we use this notation and we summarize our results like this, instead of simply just saying that the limit does not exist, we at least get some insight into some knowledge of why it doesn't exist, and this would be the preferred way to kind of write these things when we start to get these infinite limits from here on out. Much like how we had the epsilon delta definition of a function approaching a real limit, a number L, we also have the epsilon delta definition of a function approaching either positive infinity or negative infinity. I'll leave it up to all of you to kind of read over this on your own. Again, we were not doing epsilon delta as this term as a point of emphasis. Let's take a look at example 1. They ask us to determine the limit of the function shown in the figure below as x approaches negative 2 from the left and from the right. So here, thankfully, they already gave us the graph, so we can kind of analyze this graphically. So we see that this function is undefined when x equals negative 2. If we approach negative 2 coming in from the left-hand side, the function is going towards negative infinity. So the limit as x approaches negative 2 from the left, that limit is negative infinity. And we see that the limit as x approaches negative 2 coming in from the right-hand side, here the function values are shooting up towards positive infinity. So the limit as x approaches negative 2 from the right would be equal to positive infinity. Let's take a look at another one. Here we have the graph of the cotangent of theta. The cotangent of theta is undefined at pi. If we look at what happens as we approach pi coming in from the left-hand side, the limit as we approach pi from the left, the function is shooting down towards negative infinity. So this one-sided limit is a negative infinity. And as we approach pi coming in from the right-hand side, we see that the function values are approaching positive infinity. If you're curious as to what this would mean, let's say for the limit as theta approaches the pi in general of the cotangent. Well, again, technically that limit does not exist because we have a different one-sided limits. On one hand, it's going to negative infinity from the left. It's going to positive infinity from the right as we approach pi. If we had gotten a common infinity type, let's say, for example, if you look at the graph of 1 over x squared, the limit as x approaches 0 of 1 over x squared, as we approach 0 from the left, it's approaching positive infinity. As we approach 0 from the right, it's again approaching that common positive infinity. So we could say that the limit as x approaches to 0 of 1 over x squared is equal to positive infinity because both of the one-sided limits excuse me, we're approaching positive infinity. Whenever a function becomes unbounded near x equals to c, we say that the vertical line x equals to c is a vertical asymptote for the graph of f. Theorem 2.14 gives us some insight into vertical asymptotes. Let's suppose that f and g are continuous on an open interval containing c, and let's suppose that f of c is not equal to 0, but that g of c does equal to 0. And that there also exists an open interval containing c such that g of x is not equal to 0 for all x different from c in the interval. Then the graph of the function h of x, which is equal to f divided by g, has a vertical asymptote at x equals to c. This is a very powerful result. Essentially what this is saying is that let's suppose you have a limit. If you're trying to do a limit via direct substitution, if you get a non-zero number on top but 0 on the bottom, then what that's telling us is that this is going to be approaching either positive infinity or negative infinity. But at the very minimum, if you plug that number c in and it results in the computation something non-zero over 0, then that would tell you that not only do you have a vertical asymptote there, but that the limits would be either plus or negative infinity. So this also, in addition, gives us a way to find some vertical asymptotes. So we're looking for the values that make the denominator 0, but also the numerator not simultaneously 0. If we want to find the vertical asymptotes of the function f of x equals 1 divided by 2 plus x, we would start by taking the denominator, setting the denominator equal to 0, and solving. We divide both sides by 2. We get x equals to 1. Subtract 1 from both sides, we would get x equals to negative 1. This value, x equals to negative 1, makes the denominator 0, and it simultaneously would not make the numerator 0. The numerator is just a constant function 1. So we would know that the vertical asymptotes for this function would be the value x equals to negative 1. Let's take a look at part B. We want to find the vertical asymptotes of x squared plus 1 over x squared minus 1. We start by taking that denominator, setting it equal to 0. You can factor this or use the square root property. I'll factor it. Set each factor equal to 0. And we're going to get two values. We get x equals to positive 1 and x equals to negative 1. These two values make the denominator equal to 0. And you can check this, but if you plug either one of those into the numerator, it's going to result in 1 plus 1, which is 2. So they make the bottom 0, but not also the top. So we do get two vertical asymptotes for this function f. The last one we're going to look at is f of x equals the cosecant of x. And off the bat, it might not exactly seem like it lines up with the theorem that we just had, but it's probably easiest to think of the cosecant as being reciprocal sine. So we know from trigonometry, cosecant of x is the same thing as 1 over the sine of x. And now it kind of fits into our fraction form we were talking about a moment ago. Wherever the denominator is equal to 0, that's where we're going to have vertical asymptotes for this function. If you think about your unit circle, the sign is 0 here and here. It's at any integer multiple of pi. So like 0 pi, 1 pi, 2 pi, 3 pi, negative pi, etc. So when x is equal to n times pi for n an integer, those would be the vertical asymptotes for the function cosecant of x. The thing to keep in mind, this is one of the things I think that sometimes students will kind of look over, is that, again, we're assuming right now that the numerator is non-zero and that the denominator is 0. That's what's going to give us a vertical asymptote. If you plug if you plug a value in and you get 0 over 0, that's different. That's an indeterminate form. So non-zero over 0 will always give you an infinite limit, either a plus or minus infinity. You'd have to figure out which one it's going to be. If it makes the bottom 0, and if it also makes the top 0, remember that gave us an indeterminate form. If you wanted to figure out whether or not that x value that you plugged in is still going to be a vertical asymptote, you have to go back and investigate the limit to see if the function would be approaching a positive infinity or a negative infinity. For example, in number 4, they want us to find all of the vertical asymptotes of this function. We're going to start off in the same place we did before. I would need to take the denominator, set it equal to 0. I can factor this. Set each factor equal to 0. And so there's two values of x that make the denominator equal to 0. Those values are x equals to 2 and x equals to negative 2. Now, before we declare any of them to be a vertical asymptote, we would have to check to make sure that they don't also simultaneously make the numerator equal to 0. So I'm just going to call this, let me just call this n of x for the numerator. It's x squared plus 2x minus 8. If I plug 2 into that numerator, I'm going to get 2 squared plus 2 times 2 minus 8, which is 4 plus 4 minus 8, which is equal to 0. So this value here, x equals to 0, yes, it makes the denominator 0, but it also makes the numerator equal to 0. So we can't conclude from that previous theorem that x equals to 2 is going to be a vertical asymptote. What we have to do is do a little bit more investigation. We actually need to check and investigate, well, what is the limit as x approaches to 2 of this function? We would know that direct substitution produces 0 over 0, but we can analytically find this limit by factoring and canceling. The numerator factors as x plus 4 times x minus 2. The denominator factors as x plus 2, x minus 2. Notice that the x minus 2's cancel, and we have the limit as x approaches to 2 of x plus 4 over x plus 2, which would be 2 plus 4 over 2 plus 2, which is 6/4, or it simplifies to 3/2. So this function actually has a limit at x equals to 2. Graphically, what you would see is if you wanted to graph this function, so here's x equals to 2. 3/2 is the same thing as 1.5. So instead of having a vertical asymptote there, the function has a limit, and so we would have like a hole. So x equals to 2 will not be a vertical asymptote because the limit exists as x approaches to 2. If we check what happens with x equals to negative 2, if I plug negative 2 into the numerator, we would have negative 2 squared plus 2 times negative 2 minus 8, which would be 4 minus 8, which would be negative 8. So this value does make the denominator equal to 0, but simultaneously it does not make the numerator 0, so that one will be a vertical asymptote. So we just get one vertical asymptote for this. It's going to be x equals negative 2, and we have what would amounts to be a removable discontinuity at x equals to 2. It's good practice, and I think especially when you're first learning this material, to, if you have your graphing calculator, graph these and see what the graph would look like. The graph wouldn't show the whole necessarily at x equals to 2, even if you zoomed in a lot, but certainly you'd at least notice that there was no vertical asymptote there. But certainly at x equals to negative 2, I'm not sure the direction. Let me just suppose it looks something like this. But you would notice that the function would become unbounded near x equals negative 2. Let's take a look at example 5. We want to find each of the following one-sided limits. We have a rational function. If I tried to do this with direct substitution, if I plug 1 in, we would get 1 squared minus 3 times 1 divided by 1 minus 1, which would produce negative 2 divided by 0. So what does that tell us? Well, this is not an indeterminate form. This is something non-zero over 0. And because it's non-zero over 0, that means that this is going to be an infinite limit. So we already would know, because of that nature, that it's going to be an infinite limit. The question is the function approaching positive infinity, or is it approaching negative infinity at that point? To answer this question, you can do a couple different things. You could either go ahead and graph it, just visually look at it from the graph, or if you want to, you can just plug in one number that's approaching 1 from the left-hand side and see what you would get for the sign of your output. For example, if I were to plug in, let's say, 0.9 into this function, 0.9 squared minus 3 times 0.9 divided by 0.9 minus 1, let's see what we would get as a value for this thing. So I'm getting out my calculator. I'm going to plug this in. And I'm getting the output 18.9, which is a positive value. In particular, because we know that the function is going to approach an infinity, by choosing a value sufficiently close on the left-hand side, because we're looking at the left-hand approach here, as x approaches 1 from the left, the sign of that output will kind of tell you which of the infinities it's going to approach. So this will end up approaching positive infinity. If you feel uncomfortable with just using one value, you could always do like what we did before with a table of values. Pick a couple successive values to get closer. But again, having non-zero over 0, we know it's going to go up towards an infinity. And then in order to determine the sign of the infinity, whether it's positive infinity or negative infinity, just pick a test point that's close to 1, and its sign will tell you the type of infinity we're going to get. You could do the same kind of thing here. Again, substitution by 1 would result in negative 2 over 0. So we know that as we approach 1 from the right-hand side, it will be approaching one of the two infinities. To figure out which infinity it is, let me plug in something that's approaching 1 that's close to 1 from the right. Maybe I'll plug in, let's say, like 1.1. If we do 1.1 squared minus 3 times 1.1, I'll divide it by 1.1 minus 1. I'm going to plug this into my calculator. And I would get the output negative 20.9. I I know it's approaching an infinity. That one little test point gives me some sizable negative number, so I would know that this would be approaching negative infinity.